In the fall of 1894, Alexander Magruder's fiancée returned from a trip in a buggy, during which a heavy rain occurred, chilling her so thoroughly that she developed a type of pneumonia referred to at the time as rapid consumption. She feared that death was close and asked Magruder to marry her in case she soon died. He did marry her, and shortly after, she did die. A sad story indeed. Magruder was a relatively young man at the time, only 27. I don't know if he thought of human death much before this, but I do think the death of a field had been on his mind for some time. For in 1892, he began an experiment to determine just what it took to kill a field, making it unable to grow crops. That experiment is still being conducted, and the field still hasn't died. It's one of the most interesting experiments ever conducted in the field of agriculture. If you harvest crops every year without returning the nutrients removed, you're basically mining the soil until its nutrients are depleted, at which point your soil is infertile. Magruder wanted to measure exactly how long it took to mine a soil completely, so he designed a rather simple experiment where a field was farmed but never fertilized. The experiment wouldn't be of much use unless it was continued for a long time, a really long time. Fortunately, the plant scientists here at Oklahoma State University are very patient people. Magruder's experiment that began in 1892 is still continued to this day, and the field still hasn't died. Let's first take a look at the history of the Magruder experiment. This video is an excerpt from an episode of SUNUP, a television series produced by the Agriculture College at OSU.
In 1892, the first agronomy researcher in charge of the Oklahoma Agricultural and Mechanical College, Alexander Magruder, started a little experiment that's been tested by time and continues to this day.
Well, the Magruder plots are the most significant agricultural experiment that we have here at Oklahoma State University and a large part of the United States. This is the oldest continuous wheat plot in the Great Plains.
The trial was first started on a single acre where there was no fertilizer added to wheat, just to show producers in the 1800s it was good to apply some form of fertilizer. What would happen that we can actually pull down our soils to the point where we aren't producing.
And this was about the original location of the plots. But the university thought that they should grow a building where they once grew crops, so they moved the plots about a mile west, which was not an easy undertaking back in 1947. But fortunately, the experiment kept running with very little disruption.
Soils were excavated about 15 inches or so. So the soil was deposited back into the same treatment areas.
We have a manure application which gets enough manure to supply 4 years of nitrogen to an average wheat crop of the region. We have a check plot that has not received any fertilizer since the soil was broken out in 1892. We have a phosphorus-only treatment, a nitrogen, phosphorus, and potassium, and then a nitrogen, phosphorus, and potassium that is limed when the soil pH drops below a level of 5, which we've had about 2 lime applications since the beginning.
And when the wheat is growing, you can see a difference. And at the end of the season, there is a difference in yield.
These plots are amazing. The check averages 16 to 17 bushel over the last 10 to 20 years. The fertilizer manure averages 30 to 40 depending on the year, depending on the season. I've personally cut a 27 bushel wheat crop off of the check in 2008. The rest of the plots cut 50 plus bushel wheat. So amazing year, but still it's amazing to imagine that after 100 years, over 100 years of growing continuous wheat without fertilizer, it cut almost 30 bushel wheat.
With over a century of science in this ground, the Magruder plots have helped Oklahoma State University scientists with improvements to varieties of wheat that are grown all over the southern Great Plains.
When I'm traveling out of town, particularly when I go to Washington, D.C. and talk on behalf of the wheat industry and the wheat research community, I talk about these Magruder plots being here at Oklahoma State University to indicate the commitment that we and other universities in the Great Plains have to wheat research. This is just a one-of-a-kind type experiment.
And these manure plots are not applied with a spreader. We get out with 5-gallon buckets and cordon off 10 by 10 foot areas and apply to make sure that that application is perfect on a small scale across the plots.
You have a snapshot view of those modern agronomic practices up against next door to practices that would not be practiced today. And so we have an immense opportunity here to look at things that we have not looked at before in terms of gluten characteristics, maybe digestibility of the gluten.
You've got to wonder how long Alexander Magruder thought his experiment would last. 120 years later, it seems that his vision of continuous planted wheat is still showing its impact on agronomy across the world, especially in the fields of the plow-broken prairie of Oklahoma.
Now that we know the history of the Magruder plots, let's see what this century-old experience has taught us. First, let's look at the wheat yields on the unfertilized plots. The y-axis is telling us the wheat yield in bushels per acre, and the years spanning from 1893 to the present are on the x-axis. For those of you who are unfamiliar with the concept of a bushel, it's a measure of volume, and 1 bushel of wheat weighs 60 pounds. For those unfamiliar with the concept of an acre, 1 acre is 3/4 of a football field, an American football field. I find it remarkable that yields do not seem to be declining over time. This indicates that the soil is replenishing nitrogen each year and already had enough of the other nutrients to last a century or more. I should also add that as time goes by, OSU is planting more productive varieties of wheat, and that may be one reason wheat yields are level despite the absence of fertilizer. Now let's compare the unfertilized plots to those plots receiving manure fertilizer, which we know to be a complete fertilizer. Although the plots receiving no fertilizer continue to produce roughly the same amount of wheat each year, plots receiving manure fertilizer produce much more. It's clear, manure, properly applied, increases wheat yields. Now we come to the most important part, the ability of chemical fertilizers to increase yield. This is important because the amount of manure in any given region may be limited, and chemical fertilizers are often cheaper than livestock manure. Remember that when we say chemical fertilizer, we are usually referring to the fertilizer created in a large factory or mine from the earth. And when we say chemical fertilizer, we are usually referring only to nitrogen, phosphorus, and potassium, perhaps also lime. If you buy bags of chemical fertilizer in a store, they often contain 3 numbers referring to the amount of nitrogen, phosphorus, and potassium. This is so well known that the labels often don't indicate what the numbers even mean. Here's a chart showing wheat yields from the plots receiving no fertilizer in blue, manure fertilizer in red, and chemical fertilizer in light green. Notice that the x-axis refers to different decades from the 1930s until recent times. So this is over a very long time period. It's clear that both manure and chemical fertilizer produce about the same yields, with chemical fertilizer having a slight advantage. This is surprising, as chemical fertilizers do not have all the nutrients plants need, while manure does. Thus, the nutrients lacking in chemical fertilizers must already be abundant in the soil. The implication is that chemical fertilizers seem to do a very good job of fertilizing the soil over a long period of time, but that livestock manure does so as well. Finally, let us look at the rate in which the soil is being depleted of micronutrients. One would think that there would be fewer micronutrients like sulfur and copper in the plots receiving chemical fertilizer relative to the plots receiving no fertilizer. This is because the land should have had roughly the same amount of micronutrients before it was farmed, but each year more micronutrients are harvested from the plots receiving fertilizer because the yields are larger, leaving fewer micronutrients in the soil. Logically then, there should be less micronutrients in the soil of the plots receiving fertilizers compared to those receiving no fertilizer. However, this is not necessarily the case. The red bars in this graph show the concentration of 7 micronutrients in the soils receiving chemical fertilizer as a percentage of the concentration for the unfertilized plots. If the red bar is 100%, as it is in the case of iron, this means the iron concentration of the plots receiving chemical fertilizer is 100% greater than those receiving no fertilizer. That seems impossible. It would be like watching a glass fill up with more and more water the more water you drink. In fact, there are more bars with positive percentages than those with negative percentages, which means that for most micronutrients, the plots receiving chemical fertilizer are counterintuitively gaining micronutrients. We can explain the higher calcium concentrations. Notice the chemical fertilizers also include lime, which is a calcium compound. Also, before 1960, sulfur was a part of the phosphorus fertilizer applied, so that would explain the higher sulfur concentrations. But what about iron, boron, and copper? The micronutrients measured in the plots are not total micronutrients, but plant-available micronutrients. Perhaps the chemical fertilizers altered the chemistry of the soil such that more iron that was not plant-available now becomes plant-available. The blue bars show the amount of micronutrients in the soils of the plots receiving manure fertilizer relative to the unfertilized plots. There are more blue bars with positive numbers than negative numbers, and the blue bars tend to be larger overall, especially for zinc. The reason for this is simple. Manure has all the micronutrients a plant needs. So as they add manure, more micronutrients are being added to the soil. Notice, however, that the plots receiving manure fertilizer have less sulfur and iron than plots receiving no fertilizer. Perhaps manure fertilizer reduces the rate at which total sulfur and iron is converted to plant-available forms. This century-long experiment has provided us with some key insights into fertilizer. The first is that, at least on the soils in the Magruder plots, chemical fertilizers consisting of nitrogen, phosphorus, and potassium, with applications of lime, can maintain the soil's fertility for a very long time. How long? We don't know because the fields have not yet become infertile. Secondly, properly applied manure works about as well as chemical fertilizer. Third, there seems ample amounts of micronutrients in the soil, and the complex chemistry of the soil can make more plant-available micronutrients appear even when no micronutrients are being applied. For now, at least on the soils resembling those of the Magruder plots, chemical fertilizer has had a remarkable impact on agricultural productivity, and for now, seems about the only fertilizer one needs.